Welcome to the chapter on stacks. A stack is the simplest data structure in this course. You only ever touch one end, called the top. In this chapter you learn one rule, last in, first out. You build a stack in two ways, with an array and with a linked list. You also use a stack to solve a real problem. You check whether the brackets in an expression are balanced. Let's begin. Let's start with why we need stacks at all. We begin with a small task that gets messy by hand, and then we see how a stack cleans it up. This table shows what you can do after this chapter. Each row names a goal on the left, and what it means in practice on the right. First, you can predict a pop result. You can trace a sequence of push and pop calls and name the value on top. Second, you can detect overflow and underflow. You can guard a full array stack and an empty stack correctly. Third, you can map top to the top element. You can read an array stack index or a link stack head as the top. Fourth, you can build both versions in C. One is an array stack with guards. The other is a linked stack with no capacity limit. Fifth, you can use a stack to solve a real problem. You can check whether the brackets in an expression are balanced. One rule runs this whole chapter. Last in, first out. The item you pushed last is the only one you can see or remove. Let's look at a concrete need. You are checking an expression with round, square, and curly brackets. You want to know if every bracket is closed and in the right order. A closing bracket must match the most recent opening bracket that is still waiting. So you try the tool you already know, a plain array and an index you move by hand. The array holds the openers you have seen so far. Index 0 holds an open parenthesis. Index 1 holds an open square bracket. This is the newest opener right now. Index 2 is empty. This is where the next opener would go. Index 3 is also empty, still waiting for more openers. The newest opener sits at index n-1. A close square bracket should cancel the open square bracket. A close parenthesis should cancel the open parenthesis. Each closer cancels the opener you added last. When you add and remove openers by hand, the same small choices come back in every place you touch the array. Each place can go wrong. Let's read the code. This line makes a buffer named buff, with room for 100 characters. This line makes an index named top and sets it to -1. We use one convention the whole time. Top is the highest index that holds a value, and -1 means the array is empty. This line stores an open parenthesis. It writes to buff at ++ top. That advances top by 1 first and then stores. But should you store first, then advance? You have to decide every time. This line reads an opener back. It reads buff at top -. That reads first and then steps top back by 1. Or should you retreat first, then read? That is another choice to make. This last line shows the trap. If you forget to check that top is at least 0 first, buff at index top, when top is -1, reads buff at index -1. That is before the start of the array. 3 separate choices sit in every place that touches buff. Read then step, or step then read. The empty check, and the off by 1. We keep one convention. Top is the highest occupied index, the same one the stack uses below. Get any one choice wrong and you read buff at index -1, or you overwrite index 0. You need a better way. The fix is to name the discipline. Stop spreading n++ and n through your code. Put the one rule into 3 named operations. Each one guards the index in a single place. The first operation is push. It adds a value on top. The second operation is pop. It removes and returns the top. The third operation is peek. It reads the top and leaves it in place. That is a stack. Last in, first out. Every operation touches one end, the top. The index math now lives inside push and pop. You write it and check it once. You already use last in, first out order every day in 2 different places. The first is a pile of dirty dishes. You add a plate on top and you wash from the top. Plate 3 is on top now because you added it last. You never pull a plate from the middle. The first plate you put down waits the longest. The second is the browser back button. Each page you visit goes on top. The article is on top because you visited it last. Back returns the page you visited last, first. This is the same idea as undo history.